Okay guys, so let's proceed to the next part of derivations. Now I'm going to show you and how we can derive the tangential boundary equations which using our third Maxwell equations. So let's define or let's draw our interface or boundary as shown here, for example, and then let's say the interface lies along y-axis, and then the normal of interface actually pointing in positive z direction or axis. So from our previous diagram, we know that the h1t will actually appear parallel to the interface as shown here, right? That's our h1t directions along parallel to the y-axis, and also same goes to the h2t, which also pointing or propagate along in positive y directions. So we defined earlier, right? So this is our first region, this is our second regions. And let's say for this case we have assumed that there is a surface current density on the interface. So let's say I choose now the current actually pointing in a negative x directions, right? So let's say that's our JS, we assume. Why I said negative x? Because from this axis we know that the x is supposed to be point out of page x, right? So since the JS here pointing in negative x, that's why I can draw in cross symbol as shown there. So that's our assumptions of the surface current that actually appear on the boundary or interface. Alright, to find or to derive the tangential boundary equations, as I mentioned previously, we have to use the third Maxwell equations in terms of integral as shown here. Close integral the h dot dl is equal to the I enclosed. Okay guys, so this ACL actually deal with the length or the loop, or we can split that it's an Amperian loop that we have to draw ourselves that actually must close, right? So this one shows that it must close loop. So let's say we draw the loop, right? The Amperian loop, right? Alright, as shown there. So it must be closed. So the loop is up to you. It can be in any shape. Alright, you can use triangle or circular loop, so it's up to you, but bear in mind that the wrong or inappropriate structure of loop will give you a very lengthy directions. So this one must simpler one. So just use the rectangular loop as shown here. So let's define our first edge. Up here is your first edge, and here is your second edge, and third here down here your third edge, and lastly will be your fourth edge. Alright, so let's assume that the first path, the path that parallel along the y-axis actually has a length of L. Let's say we define the path, which is path 1, 2 and path 4, 3 now, has a length of L. And also let's say define our the path of 1, 4 and 2, 3 here has a height of H. Let's say, alright, so that's our assumption now. So based on this ACL equation, we have to split, right, the expressions or the integral part into four different paths, since we have four different paths, right? 1, 2, 3, 4. So we are going to have four different path integrations as shown here. The first one from, let's say, from 1 to 2. I have here 1 to 2 and a h dot dl. Second one from 2 to 3, or second path from 2 to 3, again the h dot dl number 2, this one the L number 1, and then third one from 3 to 4, again the h dot dl number 3, and lastly you have to add the last part of integrations, which from 4 to 1 back to original location or positions. So here you're gonna have h dot dl number 4, and now we have to calculate the current enclosed within this Amperian loop. Okay, guys, so based on our previous knowledge that we learned, we can simply find the I enclosed for the case of surface current density by applying these integrations, the Js dl. Okay, make sure for here we have to over dl, right? The integrations for the case of volume current dot ds. All right, so now let's say we just assume there is a surface current density on the boundary or the interface, so that should be how we find the I enclosed within the specified Amperian loop. All right, okay guys, so let's analyze one by one. So you can see from here, for the first path, actually from 1 to 2, the only h that exists only h1t, isn't it? So now you can simply change this h is equal to h1t, which actually pointing or propagate along in positive y direction. So here you can simply change to y direction, positive y direction, sorry. Okay guys, and since the path, guys, here the path from 1 to 2 here lies along y-axis, so you simply change this element 1 become y dy. Okay guys, and now let's turn to the next part, our second path, actually from point 2 or h2 to the h number 3 over here. So now guys, if you see closely, for this particular path, it involves two different ht, right? Whereby the first point from here to here it has h1t, and from point here to point here it has h2t. So you can simply put here it has two value of t, h1t and also h2t, which also both of them having positive y direction. So you can simply put here positive y direction. Alright guys, so how about the path? Since the path here, guys, actually lies along the z-axis, right? So you can simply change the L2 here equal to the z dz. Okay guys, so the next path actually from h3 to h number 4. So now only h axis actually h to t. So now we can simply change the h here become h to t, and again the h to t now only flow or propagate in positive y. So you can simply put here positive y directions. Okay guys, so and then so the third path, the path here, right, from 3 to 4 actually lies along the y-axis. So just simply change the L3 here becoming y dy. And then lastly guys, for the last path, which from h number 4 to h number 1 here, so again we can see that for this particular path it involves two different ht, whereby from this point to this point it has h2t, and from this boundary to this point it has h1t. So you can simply change this h, actually composed of two t, which is h1t and also h2t, which also both of them have positive y directions. Okay, and lastly, since the path here guys lies along the z-axis, so you can simply change the L4 here is equal to the z dz, isn't it? Alright guys, so let's proceed to the limit, or I mean for the dot product between the h and the l. If you see closely one by one, now we are going to perform dot product between h and the l. Now y dot y, yes, we have this value, and then the next part here we have here y dot with z, so now we have a 0, right, because y dot z is 0. And again for the third part here we have y dot y, so yes, we have this output. And lastly for the last path. Now we have y dot z, so now we are going to have a 0 output. Alright guys, so let's simplify the whole equation. Alright, so now let's focusing on the two paths that only exist now, which is path 1, 2 and path 3, 4. Right, sorry for that. Okay, now integration, the first one here, h1t, right? So here just put h1t dy. Okay guys, since we have assumed that this path have length of L, so let's assume here is your origin. So now the L changes from 0 to L. So now we have a 0 to L, and then plus for the second or third path down here from 3 to 4. Now we have h2t as obtained earlier. So now we have h2t dy, and now guys the limit actually changes from this point to that point, whereby here we have L until 0, is it? That's the flow, right? So now we have L to 0 again, equal to lastly the I enclosed within this Amperian loop. So now we are going to set the limit, which the L that involve actually 0 to L. So now here just change the limit of I of Js here 0 to L. Now we have Js dl, is it? Okay guys, all right, so you also can simply change guys this dl equal to y. Since y, because the current density now lies along the y-axis, so actually here we can simply change to dy. Okay, so if you proceed guys to the end, we'll see that for the first and second integration part, you can see here we're gonna have here the h1t L, and now since got a negative, right, L to 0, so we have a negative. Now have h2t L, and lastly gonna have here Js L. Okay guys, so let's simplify and reduce the number of parameter here. So now we can simply delete all this term. So finally we're gonna have this equation h1t minus h2t equal to Js. Okay guys, this is our final expressions of tangential boundary equations. Right, let me write down for you the name. Here is our tangential boundary equations that deal with surface current density appear on the interface. Alright, okay guys, in the case of non-surface current exists, yeah, on the boundary, so you can simply replace this Js equal to 0, and which will result in this final equation. Case of Js equal to 0, so this is our final expression. h1t will equal to the h2t. Okay guys, so I hope you can try out yourself and make sure you really understand the flow and familiar with the steps. And let's try afterwards using these two boundary equations to solve any magnetic boundary conditions problems. Okay, so all the best for your study, and thank you.